All right, so here's the definition of a horizontal asymptote. Hopefully this makes sense. If not, maybe worthwhile to go back and take a look at the discovery problem from 3.17. But here it is. So the horizontal asymptote is an invisible line, y equals b, for the graph of a function y equals f of x, so just some function f of x, if my function f of x approaches the value b as x approaches positive or negative infinity. In other words, we want to know what is occurring to our y values as x approaches negative infinity, means as we're moving far to the left, or as x approaches positive infinity, as we're moving far to the right. And if it is approaching a particular value as we move to the left and as we move to the right, that's what's called a horizontal asymptote. And so we can say that f of x will be approaching that particular value b. Now, the way that we have looked at this so far is by making tables of values where our x values are moving towards negative infinity and towards positive infinity, and seeing if there is a particular value b which the y values approach. And we'll do this with a couple of different examples to see if we can figure out what the rule should be for how to determine if there is a horizontal asymptote and then what that horizontal asymptote is. So let's go ahead and take a look. All right, so here are the three functions that we looked at. And what we want to do is we want to make a table of values where our x values are going out to the left very, very far and out towards the right very, very far. In other words, as x is approaching, so here this is x approaching negative infinity, and this over here would represent x approaching positive infinity. And we want to get an idea, we're asking ourselves, we're curious, what are the y values? In particular, what are the y values approaching as we move farther out to the right and farther out to the left? And once we do so, if we can determine what that particular value is that it's approaching to the left and to the right, we can say that that is our horizontal asymptote. In other words, the line y equals b, if it's approaching b from the left and from the right, is going to be the horizontal line that my graph tends to as we move to the right and to the left. So if you have not done so already, complete a table. You can use the same values here, 10, 100, 1,000, negative 10, negative 100, negative 1,000, for all three of these functions. And your goal is to determine what the horizontal asymptote should be for each. And then you want to make a conjecture as to how you can determine the horizontal asymptote by looking simply at just the degree of the numerator and denominator and the leading coefficient of the numerator and denominator. All right, so go ahead and complete that on your own, try and come up with the rule, and then we'll take a look together. All right, let's start with f of x here, and as you can see, as x approaches positive infinity, my y values are getting very, very, very small. In fact, when I input 1,000, it's so small that it's just not even worth writing because it's practically 0. And the same occurs as I move to the left, right? As x is approaching negative infinity. Again, my values are just becoming incredibly small. So what we notice here is as x approaches positive infinity, f of x is approaching 0. And as x approaches negative infinity, again, f of x is approaching 0. So since we are approaching 0 as we move to the right and to the left, what we're going to say is that our horizontal asymptote is the line y equals 0. So when we're graphing our function, we can draw this dotted invisible line through y equals 0, which is, of course, just the x-axis. And if you look at the graph of this function, you'll see that as I move far to the right, and far to the left, my function is getting closer and closer to the line y equals 0. All right, for g of x, I get something slightly different. As I'm moving to the right, as x approaches positive infinity, it appears as though my y values are getting closer and closer to 5. I can really see that here in this last step. And the same is true as x is approaching negative infinity. Again, the y values are approaching 5. And so I can conclude that I do have a horizontal asymptote, and that horizontal asymptote is the line y equals 5. Now, moving on to h of x, I see something that looks a little different. As x approaches positive infinity, my y values are growing pretty rapidly. So I would also say that my y values, h of x, approaches positive infinity. And the same is true as I move towards the left. As x approaches negative infinity, h of x also seems to be approaching negative infinity, getting more and more negative. So there's no one value that my y values tend to as I move far to the right and far to the left. So here I'm going to say there's no horizontal asymptote. I can't draw a horizontal line that allows me to show what happens to my function as I move far out on the ends of the graph. So here there is no horizontal asymptote. Okay, that's great, but I don't want to make these tables every time I need to figure out the horizontal asymptote. So let's think about why is it that this function ended up with a horizontal asymptote of y equals 0? Why is it that this function had a horizontal asymptote of y equals 5? And why is it that this function had no horizontal asymptote? And to do this, we're going to look at the degree and leading coefficient of the numerator and denominator. So let's start with f of x. Notice first the numerator. It has an x squared and a negative 1. Well, remember, we're considering what happens as x approaches negative infinity and positive infinity. So very, very negative and very, very positive x values. Clearly, when I square that positive or negative x value, this negative 1 is going to have very little influence on the actual value of the numerator. So I really just want to think about, well, this really represents the numerator when x becomes very negative or very positive. And in the denominator, I only have this one term, so clearly this is what dictates what the denominator is when x approaches negative and positive infinity. So now consider the difference between the degree of each of these leading terms. This is squared, and this is to the 4th power. Well, what's going to be bigger, 1,000 to the 2nd power or 1,000 to the 4th power? It's not even close, right? Raising something to the 4th power when I get really big x values is just going to dominate this poor x to the 2nd power. In other words, the denominator is going to get much, much bigger than the numerator. What happens when your denominator is way bigger than your numerator? Yeah, those values are really, really small. So as x approaches positive infinity and negative infinity, the denominator is just going to dwarf the poor numerator, which means our values are going to get smaller and smaller, and we're going to get closer and closer to the line y equals 0. It's important to notice that when I raise something to the 4th, it's getting so much bigger, so much faster than when I raise something to the 2nd power. So as x is increasing, this denominator is getting bigger much faster than this denominator is getting bigger. And so therefore, as we move out to the right and to the left, as x approaches positive and negative infinity, when my denominator has a greater degree than the numerator, my horizontal asymptote is going to be the line y equals 0. And that is always going to happen. Now let's look at g of x. Similarly, g of x has a numerator and denominator where the leading terms are obviously going to be more important to determining the value of both numerator and denominator when x is getting very, very positive or very, very negative. 5x squared is obviously going to be much, much bigger in comparison to 10 when x is 1,000 or when x is negative 1,000. And the same is true for the denominator. X squared is going to matter much, much more in determining the value of the denominator for these big negative values and big positive values than will x. Now, x is still going to have a little bit of influence, but ultimately, as we're approaching infinity and negative infinity, when I square those huge values, it's going to dominate that value of x. So we really just need to consider the rational expression given by the ratio of the leading coefficients. If we just consider what these are, we'll get a really good idea of what happens as x approaches negative infinity and positive infinity. Because as we do that, we know that these other terms don't really matter. So what will happen when we take 5x squared and divide it by x squared? That's actually really easy, right? X squared divided by x squared is always going to be 1 over 1. And so the value of this rational expression is always going to be 5 when I move far out to the right and far out to the left. So since these other pieces aren't going to matter that much, as I move far out to the left and far out to the right, it should make sense that I end up with the horizontal asymptote y equals 5, because that's what the leading coefficients are going to be equivalent to for those big x values. All right, so now let's look at h of x. And let's consider the big difference here, which is, of course, that as I move towards positive infinity, and towards negative infinity, my y values aren't approaching the same value. They're just getting bigger and bigger in the positive direction and more negative in the negative direction. So why is that the case? Well, look at the leading terms in each numerator and denominator here. Remember, we can say these other terms don't matter that much when x gets sufficiently negative and sufficiently positive. So what's the deal with x squared over x? What happens to that? Well, this isn't too hard to evaluate either. X squared is going to be much bigger than x, right? In fact, I can simplify this, and I can say this is really the same as x over 1, right? X squared divided by x. Well, x over 1, that's just x. What happens to x as x approaches positive infinity and negative infinity? Well, it gets really big, right? Obviously, when x is approaching positive infinity, x is of course going to be approaching positive infinity as well. And as x approaches negative infinity, we can see that x will again be approaching negative infinity as well. And so we can see very clearly why it is the case that we got the table we did. Because when we move far out to the left and to the right, what we're really looking at is the value of x squared over x, or x over 1. And so you'll notice that the x value and the corresponding y value happen to be very similar, because the only difference between them is really these other pieces here, this -1 and 3, which end up mattering very little as I move out to the left or to the right. And so we can see whenever I have a degree in the numerator that's bigger than the degree in the denominator, we're going to have no horizontal asymptote, and that is always going to be the case. So we have three situations. The numerator has a smaller degree than the denominator, in which case we'll have a horizontal asymptote of y equals 0. If they have the same degree, we can see that the coefficients of those terms end up determining the horizontal asymptote. And if the degree in the numerator is bigger than that of the denominator, then we have no horizontal asymptote whatsoever. So let's go ahead and write this down so we have it clearly, and now we can apply it to any situation that we come across. All right, so here I'm adding on to my definition. This is the definition we saw previously. And here is how we can determine the horizontal asymptote. We simply need to analyze the leading terms of the numerator and denominator. So I've written them in general, right? So here's my leading term for the numerator, my leading term for the denominator. So A represents the leading coefficient, M is the degree of the numerator, B is the leading coefficient for the denominator, and N is the degree. So if M is greater than N, and you might write above this if the degree of the numerator is less than the degree of the denominator, then the line y equals 0, the x-axis, is the horizontal asymptote. We saw that previously. If the degrees are the same, as we saw in the second example, if m and n are the same value, then the line y equals a divided by b. In other words, just the relationship between a and b, right, the leading coefficients, is the horizontal asymptote. So we saw that example where we had 5 and 1. 5 divided by 1 is 5. And if m is greater than n, we saw that in the third example, there is no horizontal asymptote, right? The y values will approach either positive or negative infinity as the end behaviors, all right? So there will be no horizontal asymptote there. And those are the only three options, okay? So it's pretty straightforward. All right, so you might want to take a second to digest this, really make sure you understand it, and then go ahead and press play, and we'll take a look at applying these in a couple of situations. All right, so now we can put it all together. You're going to find the x and y intercepts, the vertical asymptotes, and you will make sure you check for any point discontinuities, as we discussed in class earlier this week, and then also find the horizontal asymptotes for each of these functions. So go ahead and try f of x on your own first. Press play. We'll take a look at the solutions, and then you can work through g, h, and p on your own. All right, so let's take a look at f of x here. Pretty straightforward. X-intercept is the point 2, 0, because when x is 2, that makes my numerator 0. The y-intercept, meaning when x is 0, gives me a y value of -1/2. The vertical asymptote is the line x equals -1, because that will make the denominator equal to 0. And this is not a point discontinuity, because the numerator won't be 0 as well when x is equal to -1. So I just have a vertical asymptote. And the horizontal asymptote, I notice that the leading terms have the same degree. And so that means that the leading coefficients are going to determine my horizontal asymptote. And this has a leading coefficient of 1, a leading coefficient of 4. So my horizontal asymptote is the line y equals 1/4. All right, so you should go through and complete this for G, H, and P. You should have answers that look just like mine. And if you'd like to make sure that you are ready for tomorrow, you can go ahead and try graphing each of these functions using the key characteristics that we have here.